Trapezoid is quite a fascinating little shape, and is actually a shape that seems to be made up of many other shapes inside of it. Like when you look at this one, I can see kind of a square here, right, a rectangular shape, and then I can also see a triangle in there. And actually, depending on the type of trapezoid, there are many different iterations of that. Here, you can see that triangle. You can see kind of a rectangular shape. You can see another triangle. The amazing thing about this, no matter the variances of this, there is only one beautiful formula that covers all of them. And what I want to do is help you to know where it comes from. We know where base times height comes from, or 1/2 base times height. But this formula seems to be fairly elusive as to where it comes from. So we're going to look at that for a minute or two. I also just want to say that what is a trapezoid? It is a quadrilateral that has exactly one set of parallel sides. So it's not a parallelogram, it is a trapezoid. There is one set of parallel sides. And there's a special one called the Isosceles trapezoid. And what makes it special is that two of its legs are congruent. The two parallel sides are here, and then we have the two congruent legs. And if you think about it, if we kind of extended these, you would see that maybe once upon a time it was a trapezoid and that someone has truncated it or cut off the top of it. But what's going on inside of that is there's a line of symmetry that's very important to us. And we get kind of identical angles, base angles, and angle values. That's going to be very helpful in future questions. So in an attempt to explain where it comes from, I want to kind of walk you through some different techniques for doing that. The first technique we're going to do is called the doubling technique. And what I'm going to do is I'm going to take that original area of a trapezoid, whether it be of this type or of the other. And then what I'm going to do is double it. So in other words, I will take this area or this original area and kind of flip it on its back and place it into position. Now you'll notice that when we do that, a shape that we already know a formula about, we already know the formula for a rectangle. We can find the area of a rectangle. And we also know the area of a parallelogram, don't we? And so we can calculate those areas physically. And what would they be? Well, it would be the height times the base. Notice this base, because from here to here is that base 2. Here to here is that base 1. So together it's base 1 and base 2. And so it's this times this, but we divide by 2. Isn't that awesome? So by doubling a trapezoid, we either make a rectangle, and it's just base times height and divided by 2 because we only want half of it. Or when we doubled that trapezoid, we got a parallelogram, but its formula is the same, isn't it? It's the base times the height divided by 2. This is known as the doubling technique, and it's a way of just making sense of where that formula came from. If I take those original guys, either one, and double them, then I get a shape I recognize, and I know exactly what half of that is, and so it's 1/2 of that height times base 1 plus base 2. Let's look at another method for understanding. This technique is called the halving technique, to do 1/2 of it. So instead of doubling, the concept here is we're going to pull out a pair of scissors and cut it right down the middle, no matter which way it looks. And we create a piece up here or a piece up here that we are going to drop right into the spot that we want it. So when we do that, we do create a brand new shape. This one we create a nice rectangle with the same area as the original trapezoid. This one happens to create a parallelogram of the same area as the original trapezoid. And let's look at the calculation of this. This would be a base, right? and another base would be added together. And then the height, though, wouldn't be the normal height. It would be half of that height, wouldn't it? So it would be 1/2 the height, base 1 plus base times base 1 plus base 2. Same thing would be true here. This here would be half of the original height, but the bases would be both of those added together. And so there is our formula again. Isn't that just amazing how it keeps showing up? Is that new halved area is 1/2 the height times base 1 plus base 2. And the same thing would be held true here. I really, really love these relationships because they help me to understand the idea of I dissected, it created a rectangle. That rectangle, how would I calculate its area, is 1/2 of the height, 1/2 of the height times base 1 plus base 2. How sweet it is. I'd love to show you one more way, kind of using an algebraic way. And the idea is, as I mentioned earlier, that trapezoids can be cut into lots of different things. This person cut it into a parallelogram and a triangle. This person used 3 different triangles. This person used 2 triangles. This person used 2 triangles and kind of a rectangle. So what's cool is no matter how we cut this up, that formula that we've already derived, 1/2 the height, base 1 plus base 2 times that, will take care of all of these, no matter what you see as a shape, as long as you have height and the 2 bases that come from the parallel sides, you're good to go. So let's show you how the algebra plays out. This is quite a bit of fun. So I'll do it just using the idea of 2 triangles. Let's do this triangle here and its partner down here. So let's find those 2 areas. The area of the black triangle would be 1/2 its base times its height. Its base would be B1 right here. And while its height is kind of in an awkward place, it would be this, which is just the h, right? It would just be that h, the same as the other triangle's height. And that would calculate all of this region for us. In a likewise manner, the other triangle would be 1/2 its base times its height. And its base would be B2. And again, its height is that same h, isn't it? So if we were to find those 2 areas added together, we would get our area of that original trapezoid. Here's the cool thing, though. So if we took this guy and this guy and added them together, look what we get. 1/2 B1H plus 1/2 B2H. Do you see how there's a 1/2 in both of those? Let's highlight that so you can see it. There's the 1/2. So let's take that out. Do you see how there's an h in both of those? So let's take out the h. And what would be left behind in this group, what would be left behind would be B1, and what would be left behind here would be B2. And magically, there it appears once again. And honestly, no matter how we cut this up into squares, rectangles, triangles, if we calculated all of the little pieces along the way, it would always give us this beautiful formula. Sometimes the tempting thing is when you look at this is to think, oh, a square and a triangle. You can do that, but let's just go with our formula, this beautiful formula. 1/2 the height, base 1 plus base 2. So 1/2, our height will be 8, will be the height. And then this top base will be an 8, won't it? And this bottom one would be a 14 and an 8 for 22. And all of those things are taken into account, and I get a 120 centimeters squared. Very simple. Now, in this next one, I have my height. I see it. I have one of my bases. I'm missing this bottom base, but I know this is 8, and I'm missing this part right here. is unknown, but you recognize that, don't you, as a Pythagorean relationship? A 5, an unknown amount, and a 13. You do the Pythagorean theorem and you're going to get 12. You knew that. And so ultimately it is 1/2 the height, which is 5, one of the bases and the other base. Notice that's a 20 there. And all of that turns out nicely to be 70 centimeters squared. So we're starting to mix in some of the previous things we've learned. When I look at this one, the 60 pops out to me. And so I'm going to use my 30, 60, 90 relationship telling me that this would be 4√3. That also tells me this part, tells me this because of the dash marks, and it tells me this. So again, I could do this as a square and a triangle, but let's keep with our formula. 1/2 the height, base 1 plus base 2. Our height is 4√3. Our bases are a 4√3. That's the top one. The other base is a 4 plus a 4√3. You're not liking the messiness of this too much, but let's get with it here. 8√3 plus 4. And then when we multiply this out, we get 16, the square root of 9, plus 8√3. This number you know to be a 3. And so 3 times 16 is 48 plus 8√3 centimeters squared. Now, most of you aren't going to like that too much. You'll probably just go to a decimal, and the decimal equivalent or something close to it would look like this. So I guess there's some messy things in here, but that's just because we're working with the square root of 3 when we did this. But there's the top one, and there's the bottom one. There's base 1, base 2. There is our height. And we just do the math and keep things clean, and we get all our way down to here. This next one represents a lot of ones that are like this that a lot of students struggle with. I want you to notice, first of all, these dash marks. This does tell us that this is an isosceles, and that's really important. Why it's important is because it will be symmetrical on both sides. So whatever's happening on the one side is happening on the other. And how does that help us? Well, if this is 6 from here to here, that means this is 6 from here to here, leaving us 2 more. And it's important that one of them would go to this side and one would go to this side. And that's because of the symmetry. So to get our height, because that's what we're missing, we have a nice little right triangle here. 1 squared plus x squared equals 3 squared. When we solve this, we get the square root of 8, which is 2√2. Now we are able to, so that's our height here. Now we can do the math. 1/2 the height, base 1 plus base 2, and we get 1/2 our height, which is 2√2. That's going to divide up nicely. And then the top was a 6 and the bottom was an 8. And you can see that we're dividing by 2 and that we are multiplying by 2. And so those cancel out nicely. When we multiply those together, we just get simply 14 square root of 2 centimeters squared. Or if we put that to a decimal, approximately 19.80 centimeters squared. So the key to this one, friends, was that because this was an isosceles, those numbers on both sides were going to be balanced evenly, because half would go to one side and the other half would go to the other. Let me end with a dissection, which means to cut and move things around. I'm going to dissect it down the halfway mark. That means I'm going to take this piece and land it nicely into this particular spot, just like this. And so now I have a parallelogram that has this particular look. And the area of a parallelogram is its full base, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, times its height, which is 1. This is just 10 centimeters squared. Pretty simple. And I don't know if, I mean, just for the sake of testing, let's go back to our original guy. Let's do it using the other formula. 1/2, the height would have been 2. And then this base is a 2. This base is 1, 2, 3, 4, 5, 6, 7, 8. This would be 10 times 1, which is 10. Cool.